Well, we want to analyze card shuffles with Markov chains, although we know that there are various methods for shuffling, such as top-down approach, riffle shuffle, overhand, and do pile shuffle. We just focus on two of them, top-down approach and riffle shuffle, and compare them. By the way, we use Markov chains, so we provide the modeling and methodology of Markov chain, permutations, and states, and we are providing some approaches to get the better result for reasonably well, the fairness as much as possible without any favor of ordering for card games.
Now I'm going to introduce the basic modeling of card shuffling. Firstly, start with order and shuffle. A deck of n cards can be ordered in n factorial ways, and the outcome order after shuffling depends on the following factors. First is a number of cards on the deck, and the second is the input order. The third is the type of shuffle, which is the method we use. And the last factor is number of shuffle. Our aim is to look at the outcomes when we vary shuffle method and irritations. For permutation, we consider the initial order is random, and we use the bijective function as an expression of a permutation. For example, pi equal to 2, 3, 4, 5, 1 represent a permutation instead of an outcome order. To be more specific, changing an order from 1, 2, 3, 4, 5 to 2, 3, 4, 5, 1, as well as from 3, 5, 2, 4, 1 to 5, 2, 4, 1, 3 will be written at pi equal to 2, 3, 4, 5, 1. Both, where each element of pi represents the sequence number of initial order corresponding to the outcome order. For probability distribution, any shuffle have n factorial permutations that brings n factorial probability distribution on the sample space. The probability distribution varies with shuffling method. For example, we shuffle on 6 cards 1, 2, 3, 4, 5, 6 for one time. Different method brings different situations. If we use exact shuffle by moving half of the cards from the front to the back, there would be only one probability distribution as 1, while others are 0. On the contrary, if we randomly shuffle by moving random number of cards from the front to the back, there would be 5 non-zero distribution, where the sum of them is 1 and others are 0.
The goal of the project is to figure out how many times do we need to shuffle a deck of cards to make it sufficiently randomized. To answer this, we have to find out what do we mean by sufficiently shuffled. We can view the shuffle method as a random walk on the group of permutation Sn, which apparently has an underlying Markov chain. For the shuffle method topping shuffle, and actually other popular shuffle method, repeat shuffling will make all permutation possible, which means it's a regular Markov chain. And apparently it's also a finite Markov chain. Therefore, it converges to the uniform stationary distribution, and that's what we see sufficiently shuffled. Here's an example of how will the distribution be like after shuffling on only 3 card stack, and the Q means shuffle method we choose, which is topping shuffle here. As we can see, after multiple times of shuffle, the distribution is becoming uniform, where each permutation has an equal probability. Now the work left is to estimate how far we are from that uniform stationary distribution after k shuffles. The way to measure the difference between two probability distribution Q1 and Q2 is by variation distance, defined as the diagram shows. Hence, what we are looking for is the value of k, which makes the variation distance of q to the k and the uniform distribution close to 0. And for topping shuffle, we have lemma 1. The variation distance is less and equal than the probability that strong uniform time is bigger than k for all k bigger than 0, and also lemma 2 here, as the diagram shows here. Thus, we get distance after n log m plus cm times shuffle is smaller and equal than e to negative c, which is a small value. So we can see that now it is sufficiently shuffled. If we choose c equals to log 4 and ending n equals to 52, it will be 278 times needed to make a deck of cards sufficiently shuffle when using topping shuffle method.
I'm going to analyze riffle shuffle card with Markov chain. Riffle shuffle, also known as GSR, is one of the most beneficial, realistic methods for card shuffling. In this method, we provide a cut for two parts. One of them is K cards and the other is N minus K cards. Choose K, the number of cards cut according to the binomial density, meaning the probability of cut occurring exactly after K cards is given by choosing K from N divided by 2 power N. The spots for other packets then being determinal. This means particular interleavings probability is 1 divided by K choosing from N of occurring. Probability of any particular cut followed by a particular interleaving with K size is 1 divided by 2 in power N. That it contains no information about the cut or interleavings. The density of cuts and interleavings is uniform. Every pair of a cut and the possible resulting interleaving has the same probability. The density riffle shuffle define R, that is for P in Sn, and we say R function for P, and it is defined by the sum of the probabilities of each cut and interleaving, the game, and the arrangement of the deck corresponding to P. Here I provided an example for 3 cards with deck. We're starting from 1 to 3 as the initial state. 0 and 3 is maybe that case that one packet is empty and the other is whole of the deck. I provide the table with the probabilities and possibilities of interleaving and the cut. For 2, 1, 3 occur only in cut K equals 1, which has the probabilities 3 divided by 8. There is one of 3 possibilities and has conditional probability 1 divided by 3. When we can given K is equal 1, the probability of 2, 1, 3 is 1 divided by 8. Similar analysis for 3, 1, 2, 1, 3, 2, 2, 3, 1. But it is different for 1, 2, 3 because there are 4 cuts and interleaving, which gives rise for this result. By the way, for considering all the conditional probability, this cut would have the probability 1 divided by 2. I write down the entire density with the assumption that the gap started from that order 1 to 3, that the permutation instead of ordering is provided below, using the same method for finding the transition matrix for these 3 cards and riffle shuffle is provided below too.
According to the transition matrix, we obtain the following result table after computations with Markov chain, from which we can see that for the 3 card example, we get uniform distribution after riffle shuffling 9 times. Compared with the result of topping shuffle, the probability distributions of riffle shuffles method remains equal to each other except the first and last one. This makes the probability distribution more stable, as most distributions remain equal and quickly reach a steady state. If the number of cards increase, such as 52 for normal case, this advantage will be more obvious.
The question how far away from randomness, it means nobody should not be favored than the other in the random. This means the uniform density U on Sn, each permutation has probability Up is equal to 1 divided by n factorial. We need to distance between densities. The concept we will use is called variation distance. Suppose we are given two probability densities Q1 and Q2 on Sn. The variation distance between Q1 and Q2 is defined such as the equation is below, is provided from the references. 1 divided by 2 is used for normalizing the result. It is clear after 7 riffle shuffles we are very close to the uniform distribution, but the identity is still the most likely permutation. The final results show that the exact formula for the distance for k riffle shuffles is to the uniform distribution that is provided below. It is apparent that the graph makes a sharp cutoff and is reasonably how the low is k is equal to 7, which is the reason that 7 shuffles are enough to randomize a deck of cards. Considering other calculation, we're trying to maximize the considering all subsets S of Sn and Qi. We can get that after 7 riffles with the simulation that is provided in references. The indicates that 81% of our randomness variation is resolved by 7 shuffles, and this distance between Q1S and Q2S is equal to 0.31. Is nearer to the variation distance that gets from formula was 0.334, so 7 riffle shuffle is at least required for the fairness. As a conclusion, I need to say that considering top-down approach that it needs 278 shuffles for the fairness, and the riffle shuffle that it is about 7 to 8 shuffles, at least 7 shuffles. It's better that next time that you want to go to casino or card playing, you ask the desk clerk to provide 7 riffle shuffle for you to get the fairness.